All right, welcome to week 5. Let's go ahead and start. Then let's go over the to-dos. The announcement is right here. All right, so for today, PA3.go will be doing Saturday, so are the quiz number 11 to 13. Okay, so today we'll have the quiz 11, tomorrow, the 12 and 13. And the topics today are these. Last week, you guys... oh, wait. 1 second. Okay, let me just test whether YouTube Live, the chat is working. Good. All right, so last week we were talking about web and HTTP. So the remaining components are just the web caches. So we ended at cookies. So today we're going to continue, and very good. Thank you, Yanjun. The two kinds of cache. First is local cache. The next two topics are more about trying to reduce traffic between the server and the client, or trying to reduce the delay downloading a certain object. It's called the caching. So what cache means is to store a temporary copy of certain data. Okay. So conditional get here is like to have a local cache of the web pages that we have downloaded previously. Okay. So the goal is to not send the object again and again and again if the copy we're storing here is already the latest. Okay, because as a result, we don't need to send the object, and that reduces the delay, and we also reduce the bandwidth requirement. Okay, and so saving the bandwidth is going to be good for everybody. So the way it works is this. Okay. So the first time the client downloads a web page, it's going to keep a copy of the web page on a local cache. So that's somewhere in your local disk. And in the meantime, we record the date, okay, the cache copy is downloaded. And so that when we send a request for the same page again, we carry this special line in the header field, the if modify since, and then the date, okay, of the cached copy, the day we have requested the copy the first time. And then at the receiver side, at the server side, the response will contain the no object if the cache copy is actually the most up-to-date, meaning if the copy at the server has not been changed after the date, then there's really no need to send it again back to the client, okay, because the copy right here is already the latest. So in that case, a special HTTP response message is going to be sent, and the status line is going to read like this. Yeah, 304 not modified. And in the body of the HTTP response message, it's going to be empty. Okay, so no need to send the object. And the way it works is more like this. Let me illustrate. The second time, the client here requesting for the web object sends request message and having this in the header line. If modify since the date the page was downloaded the previous time. And if the server finds that no, it's not yet modified, then send back a short HTTP response carrying the status line. And that's all. No data here. But otherwise, if the object is modified, then we send back a regular HTTP response that says 200 OK in the status line and the web object, the web page again, okay, in the body and the T. All right, so that was local cache, quite straightforward. And it's keeping a copy of the page locally on the hard disk. Now let's check out the second kind of cache, web cache. Web caches, the purpose is very much like the local caches, but the way it works is somewhat different, but not much different though. Okay. The main difference is this. In local caching, we keep a copy of the object here. Okay. But now we keep a copy of the object here in the web cache, or also known as the proxy server. Web cache or proxy server. Okay. And in conditional get, we still need to send HTTP requests to the original server. It's just that the original server decides whether to send the object with it or not in the response. Okay, sometimes yes, sometimes no. So we save a little bit delay and bandwidth this way. But in web caches, the goal is actually trying to satisfy some client request such that there's no involvement of the original server required. Okay, so some of the clients doesn't need to reach the original server to get the object. And this is done by keeping a copy of the objects somewhere in the middle at the proxy server. Okay, so the way it works is this. Users will set the browser such that for all web access, let's go through the web cache. So subsequently, the browsers will send all HTTP requests to the web cache. So send it to the web cache. If the object, the page we're looking for, is already in the cache, proxy server sends the object back. So you see, it works somewhat like a server, but it's not the original server. It's somewhat a delegate of the original server having a copy here. Okay, so object in the cache, cache return objects. Otherwise, the cache here, the web cache here, would request from the server a copy of the object. So this request will be like, the proxy server here behaving like a client of the original server. Web cache there, request object from the original server like a client. Okay, and after the object is downloaded here, the proxy server then sends the object back to the requester. So let me illustrate. If the object is not here, requests go to the original server, response comes back, store a copy, and then forward it back to the client. And what's nice about this is, look at this client down below. If the client is requesting the same object, it's a hit here at the cache. Server here sends back the object directly without going through this segment of the internet. So, cache there acts both like a client and a server. As a server, so that it served the original client the objects. As a server, because if there's a miss, it will be requesting the original server for a copy of the object. Right? So, some of you might see already, right? A web cache like that is actually preferred by the ISPs, which serves a whole bunch of customers locally. Usually people sitting close to each other tend to prefer fetching or tend to fetch similar content. So a lot of times ISPs might encourage you to set a web cache on your browser. Now, let's go through a few examples to detail why using web caching. Local cache, nice, reduce delay, reduce bandwidth. Through this set of examples, let me take you through what is the benefit of doing web caching. In a nutshell, a lot more delay and a lot more bandwidth saving.
Okay, thank you. You probably see from the video that my mouse is moving, but the audio is not going out. Yeah, so I muted the mic to make sure that the video's audio quality is better. But yeah, thank you for letting me know. Yeah, so we pause right here before we go on to talk about the 3 scenarios to explain why web caching. Web cache can save us more time and more bandwidth. Let's come back to Liang Yu's question about where are we storing the local cache? you know what? The local cache, thank you. The local cache is stored on your hard disk. When you install a browser, usually there's a folder there keeping the cache. That's why on Google Chrome or Safari, there are always these settings. You could say that you keep the cache or flush the cache. So when you do those things, then they remove all these copies of web pages that you've previously downloaded from that part of hard disk. So local cache is stored on your machine's hard drive. Now, web cache is actually stored somewhere in machines in the middle of the internet. Okay, it's not really local to you, to the end user. Okay, so that's the main difference between local cache and web cache. Now let's move on to the example, and let's go through 3 scenarios and see why web caching is better.
Good. The example. Setting is this. Servers up here, client down here. So they're part of the institutional network here. And the servers are connected to the public internet. And the internet connects to the institutional network through an access link. Now let's assume that the clients here are browsing the web, requesting objects down from the server. The average object size being 100 kilobits, and the average request rate being 15 objects per second. Then multiply the two, you get the average bit rate, okay, coming down this way, right? And that is 1.5 megabits per second. Now, let's see. Round-trip delay from the institutional router to any of the origin servers and back. That's set at to 2 seconds. And the link, access links rate, 1.54 megabits per second. And the local area network link rate, 1 megabits per second. Now with these, we will be able to calculate the local area network's utilization. 1.5 meg divided by 1 gig, that's 0.15%. But here, 1.5 meg divided by 1.54 meg, that's very close to 99%. And that is a problem if you recall. There's this component called queuing delay in the internet nodal delay. For transmission over a hop, there are 4 components: processing delay, queuing delay, transmission delay, and propagation delay. And the queuing delay is very sensitive to the utilization on the link here. Right? So let me take you here. Queuing delay. Just in case you kind of forget about it. It's very case dependent, and the determining factor is the utilization, which we call back then when we were talking about internet delay, the traffic intensity. So this is the amount of input, and this is the output capacity. You see, utilization again. When this is very small, queuing delay also very small. So as it approaches 1, delay becomes large. When it exceeds 1, delay is actually approaching infinity up here. Right? So close to 1, close to 100% delay, just very low. Okay. Let's come back here. Therefore, if we want to calculate the total delay of web request and object download, it will be round-trip delay here, plus round-trip delay here, plus round-trip delay here. 3 components: internet delay, access delay, and LAN delay. Internet delay, we already defined it. Just make it simple. Just say that it's only 2 seconds. But hey, here, fully utilized link with high queuing delay, it's going to be very long. Let's just say that it takes minutes. It could be even higher. And the LAN access delay. Now this is very low because utilization is super low. So let's say microseconds, right? So 3 components, which one dominates? Yep, queuing delay on the access link dominates. So bottleneck where? Here. in terms of delay performance. How do we fix this? Let's look at the second scenario. In scenario 2, let's try to address the issue here, because this is the bottleneck link where the delay came from mostly. And let's blow it up 100 times. How about that? So using a fatter excess link there. The result is that the excess link utilization is also reduced 100 times. Less than 1% utilization, you can imagine the queuing delay being very, very short. That brings this component of the delay down to milliseconds. Now, why millisecond? If you recall trace route testings that we did earlier in chapter 1, right? What was that? Quiz 3 or quiz 4, isn't it? Yeah, most of the delay we see between two routers are what? Tens milliseconds and maybe 100 milliseconds at most. So if there's not going to be much queuing delay, yeah, the delay is at this scale. So 2 seconds, milliseconds, microseconds, which of these three components dominates? Obviously, 2. And from scenario 1, we have minutes of delay, to scenario 2, we effectively bring down the total delay. All right, great. Is there any catch? If you think about it, hey, bringing the excess link capacity up 100%, that is actually not cheap. So increasing excess link speed, no, not cheap. You need to purchase the new cables, of course, but you might also need to do groundwork. Okay, remove the old cables, install new ones. Just think about the labor cost there. And in addition to that, you might need to upgrade the routers there connecting the high-speed link, just so that you can accommodate potential traffic volume. So, yeah, very costly. Now, in scenario 3, let's see if we could introduce something else instead of blowing up the capacity in the bottleneck link. Web caches.
Oopsie, wrong click. So let's pause here for a little bit because scenario 3 is going to be slightly long. The video is about 8 minutes. So you'll see we need to introduce a term that's a little bit special called hit rate.
In scenario 3, instead of blowing up the access link, let's install web cache here. I'm calling it the local web cache because we are very close to the clients. All right. Oh, and yeah, I meant local web cache here. Okay. So that you are not confused with the local cache we've talked about in conditional get, where that cache is actually very, very local on the hard disk of the user, right? So we are only slightly local here, so to speak. Good. So everything else stay the same. All we did is just install the machine. Now, if I ask you, changing this to 154 megabits per second versus adding a server machine, which one is more expensive? Yeah, you probably guessed, right? Labor costs, routers are expensive, cables sometimes can be expensive depending on the distance between the physical distance between the two routers. For your information, this could take millions of new Taiwan dollars. But installing a high-end server machines, it only takes this much new Taiwan dollars. So that's about 2 orders of magnitude difference. Yeah. Installing web cache, so much cheaper. Great. Now, let's see if the delay is also going to be better. Or maybe if this is cheaper, then delay is going to be worse. Now, let's try to calculate this. We know the LAN utilization, and so maybe the LAN delay is also about, microseconds. But excess delay, well, we'll have to know the excess link utilization in order to estimate the excess delay. Therefore, question mark, therefore we couldn't quite yet estimate total delay, right? But then, so this has something to do with the traffic that needs to be brought down this way, right? How many objects will be coming down this way? That seems to be the question. And if you think about it a little bit more, isn't that depend on, for all these web requests we send to the proxy server, how many of them are going to be satisfied locally? Therefore, we could just, transmit the object from the web cache through the LAN to the client without going all the way up to the servers. So that is this thing called the hit rate. Okay, amount of the proportion of the request being satisfied locally, that's the hit rate or the success rate. Yeah, let's suppose the hit rate is 0.4. Then we see 40% of the requests will just stay here. Only 60% goes out and back. Great. So we know then the access link here, the utilization is 60% of the access link, 60% of the scenario one. And how much is that? 60% of the traffic, then it's only this much traffic on the 1.45 megabits access link, only 58%. So we cut the utilization from 99% to 58% if we ended up having this hit rate. Now let's calculate the total delay. So 60% of the time it's going to be long delay all the way to the server and back. 40% of the time just on the local LAN. Now, local LAN delay, we've seen earlier, microseconds, but I'm using the milliseconds here just to take into account the traffic here. So if we go out, request object down to the web cache, and then web cache serve the local client, we have one copy down here and another copy down this way. So the LAN here, the traffic potentially could also be higher. So let's use milliseconds just to be safe and take that extra traffic into account. Now, for the 60%, we'll have to go out and back, right? So this is very negligible. This part is what? The key component. This part, 2 seconds, we know for sure. So what's remaining is just the delay here on the access link with 58% utilization. Well, how much delay is this? If there's a lot of queuing delay, we go minutes. If very, very low, only 1%, we go milliseconds. So minutes, milliseconds, well, that's, pick, say, tens milliseconds or hundreds milliseconds, right? So I'm trying to be a bit generous here and use 10 milliseconds only. And so total delay here about 2.01. And 60% of that plus 40% of milliseconds. The dominating component is the 2 seconds. So you see here, the overall total delay on average is going to be about 1.2 something seconds. Is this better than scenario 2? It is, right? Scenario 2, you have at least 2 seconds. So what's amazing about web caching is this. The benefit is not just that it's cheaper, but the delay is also lower. And the traffic coming down this way is also lower. Hey, we did not spend any money here, and we also saved some bandwidth here as compared to scenario 1. So there's more traffic can come down this way. Isn't it nice? And that explains why we need web caching, all right? It's to reduce the delay. This is also called the response time, okay? That meant the time it takes to issue the request all the way to the server and bringing down the web object. The round-trip delay of the request and response messages. It also reduces traffic, save a lot of bandwidth on the access link, and it's very cheap. Now, an extra benefit we didn't talk about is because we did not assume the uplink bandwidth of the servers being the bottleneck. If the server is poor, meaning having poor content providers out there, then, let's say that the server here is poor. It cannot afford too high bandwidth uplink. Then reducing the amount of traffic going this way also saves poor content providers some resource, some money. And so web caching there also help the poor content providers to deliver content. All right. And this could be a good thing because most of the NGOs, they might also have information to disseminate, but they couldn't provide good uplink bandwidth. And that actually gives rise also P2P file sharing. The idea of P2P file sharing is also, hey, if I have the copy of the content and another peer grab a copy of it, then this other peer can help serving the other peers. So that peer there is working pretty much like a web cache, isn't it? Like a proxy server. So you could actually think of a P2P network, a network of these proxy servers. Okay. And you saw a bit already. Next slide. Coming next is going to be the second application in Chapter 2. And we'll look at how FTP defines its application layer protocol.
Okay, so next is FTP. And caution, the FTP video is a bit long, altogether about 11.5 minutes. Let's see if you guys can survive a long video like that. And everything about FTP is going to be in this video. So pay attention to the communication model. Is it client server or P2P? We need a socket to connect the components that need to communicate. Which port is it on? And what kind of transport protocol they use? And the messages they're sending, formats, syntax, semantics of these messages. Okay.
FTP, the File Transfer Protocol. This is the second application layer protocol we're learning here. So, see if you can identify what is the communication model, what is the structure between all these entities involved, and what is the underlying transport layer service, and what are the message types, syntax, semantics, and how are these messages exchanged? Pay attention to these. So first of all, what is the communication model? You see here, client server. Client is always the side initiating transfer. So over here, this side. And server is always the one that's far away. It's over here. All right. So what you see here is FTP is to provide transferring of files to and from the remote host. Server here is essentially allowing the users or the client access to the hard disk here. Okay, so it's a little bit like Dropbox. Okay. So a distributed file system in a way. Good. Now, file can go this way as well as this way. So you see here, it's bi-directional. Good. The protocol is defining this RFC. The number is only 3 digits. You see that this is one of the earliest internet protocols. The server there is sitting on port 21, another well-known default port number. So whenever the client needs to initiate communication, it goes to port 21, where the FTP server will be sitting on. And by the way, 21 is also the port number that Poly confuses SSH's port number on. All right, so let's take a closer look at the message exchange. So FTP clients contact FTP server at port 21, this we know, and specifying TCP as the transport protocol. So FTP there uses TCP just like HTTP as the underlying transport layer service. And then the client will try to authorize itself into the server over a control connection. So what I'm depicting here is also what's going on here. the client will establish a control connection towards port 21, okay, at the remote host. So messages saying, I want to log in, here's my password, will go on this connection. After the client logs in, it's going to browse through the directories, okay, in the remote hard disk over here. So the commands changing the directories around is going to also be sent over the control connection. When the server receives a command for a file transfer, okay, so command for file transfer also travel this way as it's also a command, so it goes down the control connection. But the server now, okay, will open a TCP data connection going back this way. Okay, so that is depicted here. The data connection running on port 20. Okay. After transferring a file, the server is going to close the data connection while this one remains on. If the server needs to send another file, it would start yet another TCP connection and send the file over there. Okay. So such separation of control and data-based content on different channels, okay, in communication, we call it the out-of-band communication. If you think a little bit more, in HTTP, there are two messages, right? HTTP request, HTTP response. Yeah, which one is data? Which one is control? No, in fact, each of these messages are both control and data. In HTTP request, we do have command, right? Get, post, head. But in HTTP response, we also have the status line. So these are obviously control. But in both messages, we also have the body entity. If you use a post commanding HTTP request, you might be sending also some data up to the server. And very classic web response, the entity body contains the web object. So in HTTP, communication is in-band. One word, in-band, right? Data and control messages are bundled together and going on just one connection. FTP, very weird, out-of-band communication. Another thing that FTP differs from HTTP is this. HTTP being stateless, but FTP is stateful. So FTP server here actually store information about the client's previous visit, including where this client at in the directory structure before the client logged out. Okay, so next time when the client wants to log in, the server will take him directly to whichever directory the client left. So the client can continue working on, downloading files or uploading file in that space. Similarly, if you log in as a client, you might get a message from the server saying, oh, you logged in previously at a certain day and certain time. Okay. So this is sometimes a nice thing to do because you might want to know if there are unauthorized login and authenticated login, meaning someone stole your password and then use it to log into the FTP server. Next are just a few examples of the messages being exchanged between the FTP client and server. So these simple comments are messages the client sent to the server. And server typically return these return codes, right? So very much like the HTTP request, the control part sends comments and necessary information to help the command to be executed at the server side. And then the server returns certain code, phrases, and explaining of the code and the phrases. All right, let's look at the example. Oh, and by the way, again, in FTP, messages are in ASCII text, right? Data, however, on the data connection could be in bytecode, all right? So control connection there is always sending ASCII text messages. And control connection there is also allowing the server to send back a status code. Okay? So these and these all on the control connection, only the data on the data connection. So let's begin. User, capital user, space, username. Hey, you guess, this must be a user trying to log in and providing the username. So this is a variable, so comment, argument. And this is gonna be sent through the control connection to the server. Server check. If the user does have an account on the server, then this is what the server sends back. 331, username, okay. And server asks, could you send me the password? So hey, a hacker might figure out the username, but not necessarily the password. So client here sends pass, again, capital, space, password, over to the server. And then the server can perform the rest of the authentication. So you see, capital, PASS, capital, USER, these are special words, okay, in the comment messages. All right, so each followed by an argument. List, this is a special command, no argument required. What it does is to return the list of files, okay, in the remote directory. So upon receiving list at the server sends, okay, here are the files in the directory. Retrieve, RETR capital, space, file name. This is now officially to ask for a file from the server. Retrieves files. The other way around, if we want to store a file, upload the file to the server, then store capital file name. Now, here are some status code and phrases the server might respond. So, 125, data connection already open, transfer starting. So this might be the server responding to a retrieve command. Okay, setting up a data connection, and then next bytes are gonna come. Or server might find that, hey, there's not enough socket to open, or there's not enough bandwidth can open, data connection message might be going back. 452, error writing files. Oh, okay, so this is this case. If the client wants to put the file onto the server, and if there's not enough disk space, or if the client doesn't have the access right, the writable access right, then the client gets this message, 452. Okay, so that's FTP. We see again, an application layer protocol defines communication model. Is it client server, P2P, or hybrid? An application layer protocol defines also what is the network structure. In both HTTP and FTP, it started off very simple, one client, one server. But you see earlier in HTTP, it kind of grows a little bit, having these proxy servers in the middle, helping with the transfer. In every one of these application layer protocols, we also need to define what are the messages to be exchanged and the order they exchange. So we see here examples of messages defined for a FTP and how they're exchanged, okay, in the previous slide. Okay, it's through the control channel, yeah, logging messages, checking directory messages. So this is FTP.
And then we move on to the next application layer protocol, which is slightly more complicated than the other two. So that you see that it's no longer just client server involving the communication. There could be layers of client servers involving the communication. So this video is about 6 minutes, and the quiz is coming up right after the video.
2.3, emails. So this application is a little bit unusual. It's supported by not only one application layer protocol, but multiple ones. And we'll talk about it. Email application. It's got three major components. First is the user agent. This is the software running on the machine closer to the users. And mail servers are the software running on more resourceful machines farther away from the users. And among these mail servers, it runs this protocol, SMTP, the simple mail transfer protocol. These we'll also talk a bit more about. Let's start from the user agent. They're essentially the email readers. They allow us to write email, edit email, read emails. Outlook from Microsoft is one mail reader that's very well known. Thunderbird, I don't know if you know about this one. This is from Mozilla. So the company that produces also Firefox, the very well-known web browser. iPhone comes with a built-in mail reader. Google is also trying to push for a Gmail mail reader. So there are so many of these email readers these days. Now, keep in mind though, the actual emails are all stored on the servers, not on the user agent these days. All right. Now the mail servers. It's got these three major components. The mailbox, which contains all the incoming messages per user. So these are the yellow boxes. When emails come in, they will be sorted out and then put into the email boxes depending on who the receivers are. Second component, the message queue. Those are the green queue over here. So messages that are going out will all be stored here temporarily and waiting for the receiving mail server to open up and then accepting the emails. So SMTP protocol there is to allow the sending server and the receiving server to communicate. Now here in particular, the sending server there is called the client of the SMTP protocol. And the receiving server is, on the other hand, the server of the SMTP protocol. So you see a little bit here. The SMTP protocol is to provide mail receiving service in a sense. So client here requesting service, server here allowing emails to come in. If you think about it more, it's got two levels of communications in the email application. So this is one between the end users and the local mail server. Okay, fetching email or pushing email out. But there's another level, which is among the mail servers. All right, so sending mail server is the client of the higher level communication. Receiving mail server is the server of the higher level communication. Then the SMTP protocol. So this is the actual application layer protocol defined to support communication in emails. So let's see, what are the underlying protocols and what is the communication model and what are the messages defined? TCP you see here. Therefore, SMTP is to support reliable email receiving service. It runs on port 25 and the transfer is direct between the sending and the receiving server. The exchange, very simplistic, 3 phases, handshaking, and then actual transferring of the emails, and then closing. Opening, closing, the actual transferring of the emails in between. The messages are also simplistic. They're just comments coming from the sending server, responses coming from the receiving servers. So comments in ASCII code, just like HTTP, just like FTP. Responses, status words, status phrases, status code, just like HTTP and FTP. They all run in the ASCII code. Now put all 3 major components together and let me illustrate with a concrete scenario. Alice here is sending an email to Bob over there. All right, so Alice will need to start the user agent first to compose an email. So in the email, it will need to specify the receiver. And then the user agent will send the email to the message queue, okay, in the local mail server. So that is step 2, emails going to the message queue. And then the client side of the SMTP, which is here, this guy is the one sending, And this Bob's mail server will be the one receiving. So this is the client of SMTP. This is the server of the SMTP. So client side of SMTP will open up a TC connection. Once the server is allowing the connection, then the client can begin sending Alice's email. So that email will travel, and the server here of Bob's will check whether the receiver is Bob, and therefore putting the email into Bob's mailbox. Right? So email goes to Bob's mailbox. Lastly, when Bob now joins the internet, invoke his user agent, then the agent already pre-configured to connect to the incoming mail server will then fetch the mail messages, and that's when Bob gets to read the email.
All right, so let's go to the quiz. So you see here that the entire string of communication from the sending user, from Alice, to the receiving user, Bob. And you see that SMTP working from the user agent to the local mail server, and then from the local mail server sending side to the local mail server of the receiving side. But it stopped right there. Okay, so last part, Bob needs to log in, okay, and fetch the emails from the receiving local email server. So that segment there between Bob's user agent to Bob's local mail server is using another protocol called Mail Access Protocol instead of having SMTP going all the way to Bob's user agent. So what do you think? Okay, is the reason that SMTP does not go all the way. So that was quiz 11. Yeah, so this should be relatively straightforward, okay? But it can be tricky, not that obvious for some of you, okay? And let's move to Slack and work on quiz 11. Those who finish early, feel free to just go, okay? Because the answer was quite easy. Oh, there. Okay, so Team 13 has already come up with several reasons. Okay, that was really fast. So let's give it a little bit more time. Okay, and in the meantime, let's go over the questions. Yanjun was asking, why the 7-bit ASCII code? It was the most popular code at the time. Nowadays, we do have ISO something and some universal code, so where we could also put symbols or characters from other languages, not just English, in the messages. 7-bit ASCII code implies also that all the characters in the messages are English, essentially. Mao here, Chun Mao is asking, does it mean that every person's computer is a mail server? You know what? From the sender side, it is a part of the SMTP protocol. Okay, it's just that we don't call the user agent, especially the sender side, a mail server. We actually call the local mail server there being the server of the exchange between the user agent to the local mail server. So in a way, user agent there of Alice, the email sender, is the client of this communication. Okay. The local mail server, it is the server, but it's also the client of the second level of communication from the sending mail server to the receiving mail server. But the user agent at the receiver side, so Bob is the email receiver. That user agent is not part of any of these SMTP exchange. Okay. That user agent is a part of the mail access protocol communication, but it's also the client side of mail access protocol. Okay, so Chun Mao, so that hopefully explains the user agents. okay, or our computer there where we run the user agents while we type up emails are still clients. Okay. I understand that now we have 2 levels of client-server communication. Things can get a little bit confusing. And Bing Ray is asking, if Bob's mail server is down, would the mail stuck in the mail queue? You know what? Yes, it will not go out. So if Bob hits send and that email goes to Bob's email server, that will get stuck in the green queue in case Bob's email server went down before a mail server can push the email out to the receiving server. Okay. If Bob's mail server is down, Bob might not read the emails that just arrived to the yellow queue there, the inbox. Okay, so if Bob's mail server is down, Bob will have trouble really sending the emails out, as well as reading the emails that just came in. And you can think of the role of Bob and Alice reversed as well, right? Bob can be sending and Alice might need to read. If it's reversed, Bob's user agent will be part of SMTP and pushing email out to Bob's local server. All right? All right. Okay, so maybe we can go through Team 13 and Team 7 solution for Quiz 11 real quick. And tomorrow when we, before we start the lecture, we can check if there are some very interesting answers here. Okay. Team 13 is saying SMTP is a push protocol and sends message to some server, but Bob's job is more to receive. And so let's see. Like a pull protocol in some way. Okay, interesting perspective. Bob's IP address might change with time. Oh, interesting. Because for SMTP to push, to send email, the receiver, the sender side needs to know the IP address. So Bob's user agent, so that machine there could be Bob's laptop, right? So if you carry your laptop around, the IP address is not fixed, right? So how would Bob's mail server know that where to establish the TCP connection? Makes sense? Mm-hmm. Bob might use different user agent to check his email and might not be online all the time. Exactly. So Bob might move to some other places and use those machines to check email, and not necessarily Bob's laptop. Yeah. So it's better that we let Bob to try to connect to the local server independently of the sending flow. Okay. Jieming representing Team 7 here. Bob may use different agent. Okay, so this is similar to point number 2 and 3 from Team 13. SMTP is push, but Bob's agent needs to pull. Yeah. So the way of communication, it seems one for sending, more convenient to push, but in Bob, the nature is more to pull. And they kind of mismatch in terms of purpose. All right, I'm seeing you guys are keying up the solutions. Okay, but time is up. So those who need to catch the next lecture, feel free to go. And I'll just address Yunqi's question, and then we'll close the session. And come again tomorrow morning, 10:20. So for most of you, bye. Yunqi is asking why there are many little yellow boxes in Bob's mailbox server. Does it mean that there are other people using this mailbox server? Exactly. For example, you and I using the something@ntu.edu.tw email address. So that mail server, I believe the host name is mail.ntu.edu.tw or smtp.ntu.edu.tw. So the host name for our NTU mail server is that. Okay, bye, Yuxiang. So Yunqi, you and I, each of us, our inbox is a little yellow box. Okay, on smtp.ntu.edu.tw. Okay. Similarly for Yuxiang, for Chunmao, for Chen Tao, okay, each of us, if you use that NTU email address, we have a little yellow box there on the server. Okay, so that's why it doesn't look like a long green long queue. In the outgoing queue, as we send email in, the NTU mail server would just push them into the queue, usually first come first serve. Some better mail servers will try to sort our emails depending on the destination. Okay, so we might be sending email to somebody's Gmail address, then all those emails going to gmail.com will be on the same green queue. Okay, to another major mail server, another green queue. That way they can have parallel connections to send emails. Okay. But the very classical mail server, the way they maintain the outgoing queue is just one long queue. Okay, depending on the mail that they need to serve at the time. Establish TCP connection, send to the receiving mail server, and so on and so forth. Okay. All right, good. So that addressed all the questions we have. I'm going to stay online for a little bit to make sure that I capture all the interaction on YouTube chat. Ciao, ciao, Boris. Oh, thank you, Shang. Very sweet of you. All right, so let me end the stream now. I see you tomorrow.